To understand the instrumental variable regression framework, we can look at this example. And here we are estimating the price elasticity of demand for cigarettes. So just remember that the demand function is a downward sloping function of price on quantity. So if you increase price here from this to this, then you lower the quantity from this point to this point. Okay? So what if specifically we want the tax to be put in place to increase the price of cigarettes? How much would we have to increase the price to reduce the demand for cigarettes by 20%? And in order to find this answer, we have to look at the price elasticity, which is the change, the percentage change in quantity, Q for quantity, divided by the percentage change in price. So what you get here in this is just a number, and this is the change in quantity per change in price. Okay? So, for example, if we are given that the elasticity of demand is negative 0.5, this means that if you want the quantity to go down by 20%, you have to increase the price by 40%. So in this case, you are interested in the change of quantity given a change in price. And you remember that whenever you want to model a change, you just take the natural logarithm of something. And the natural logarithm is just the exponent of a number, of a base number. And in the case of the natural logarithm, you have the base number of e, which is 2.1828, I think. And to get x, you just raise e to the power of this number that you get from taking the natural logarithm of the number itself. Okay, so to get this change, you transform the quantity to the natural logarithm of the quantity, and you change the price to the natural logarithm of the price. And just remember that you can't take the logarithm of something negative, so of a negative number, so you assume that both the quantity and the price are positive. Okay, so, and why do we expect that this beta is negative? It's because we have, as we saw in the previous slide, the downward sloping relationship between price and quantity. So if you increase the price, you lower the demand. So you have this negative slope. And this beta 1, this slope, tells us how many percentage the change is for the quantity given a change, a unit change in, or 1% change in the price. So this beta 1 is the change in percentage of Q, or in Q, given a 1% change in P. We have gathered data from 48 US states on price and the quantity. And to get the change, we take the logarithmic transform of these two variables. And our first and initial idea is to just get the quantity, or model the quantity, get the estimated quantity based on an intercept plus the slope. Yeah, that should be better. 1 hat of the logarithmic transform of the not the x, the price. And this is actually a wrong approach, because in equilibrium, price and quantity, they affect each other. So the causality goes both ways here, because if you increase the price, you would affect the quantity. If you increase the quantity, you would affect the price. The fact that this causality from price to quantity and from quantity to price, it goes both ways, it induces some simultaneous bias in this equation 4. Remember that equation 4 was the quantity, the demand function, equals the intercept plus the slope. Here we are looking at the population equation, and you have the price plus an error term, U, okay, which contains all the other factors which affects the demanded quantity other than price. So the reason why we have this double arrow, this causality going both ways, is because there is also a supply equation in which we model the change in price, how it causes a change in quantity supplied. And here we expect the quantity supplied to be an increasing function of, or in this case a linear function, an increasing function of price. So if you increase the price, then producers would like to increase their production in order to sell more stuff. Okay, and because of this, this process is determined by both the demand function and the supply function, then you have this price affects quantity and quantity affects price. So because we have this demand function and the effect of the supply function, then there will be a correlation between the change in price and the error term, which means that we get biased and inconsistent results, and the slope, the demand elasticity, will be biased upwards. And what does that mean? It means that if we had the price here and the quantity demanded here, we get a downward sloping, or we should have found a downward sloping relationship. So this is the true line, but what we get is a result which is a biased estimate. Okay, so what we get is really a result that is less elastic than the true elasticity, which means that we are led to believe that a change in the price is not very effective in changing the demand. And more logically, you can see that if we have the demand function here, it's beta naught plus beta 1, which is the slope, the causal effect. Let's see here, the natural logarithm of the price plus the error term u, and here we have the quantity supplied equals, let's see which notation we used. We used gamma for that one, the intercept and the slope of the change in price on the quantity supplied, the change here, plus the error term, which contains all the factors which affect the quantity supplied, except or apart from the price. So you see here that if this is indeed a causal link, if you cause the u some shock to the error term u, it falls, then you would expect the quantity demanded to fall. But since in equilibrium the quantity demanded and the quantity supplied, they must equal out, then the quantity supplied falls, and which means that the price actually falls as well. So here a negative change in the error term u causes the price to fall, and a positive change in the error term would cause the price to increase. So there is a positive correlation between the price and the error term in the demand function. This means that the beta 1 is biased upwards. Our problem is that the data points we are getting, they are a combination of these supply curves and demand curves. So we only see the cross where the supply curve and the demand curve intersect, and which means that we get all these data points which are intersections of these curves. What we would rather have is the demand curve, and we want the demand curve to be stable, but we would like the supply curve to shift. Okay, so this is supply curve 1, 2, 3, and 4, and if we get these data points, then we can trace out the demand curve, okay? Because the data points would all lie on this line. And if we have these lines, we can easily find the slope, the relative change in quantity given a change in the price. So this means that we need to find a variable that can shift the supply curve but not the demand curve. And this variable will be our instrumental variable. And this instrumental variable is correlated with prices but not with any other factor affecting the demand. So it's uncorrelated with the residual from the demand curve. And one of those variables might be the tax, because tax, it does not change the demand function. So for example, if you have the price here and the quantity here, and you have a linear demand function, this is demand, and you have a equilibrium quantity and price here. No, that should be a P for price here. And then you have the equilibrium quantity. And at first you have the supply curve here, 1, and then let's say that you add some tax. So this is the tax that you add, okay? And as a customer, you don't care about if the price of the product goes to the tax authorities or to the company. You only care about the price of the product. So given this new price, PT, the price after tax, which is higher, it means that the demand for the product is lower, okay? Which means that given the fact that quantity demanded and quantity supplied, they both have to intersect, they have to be equal, then we get a new supply curve, ST, for example, for tax. So this tax, it has shifted the supply curve because it has shifted the price, and then the price shifts the quantity demanded. Okay, so this sales tax is therefore a relevant variable for us to map out points at this demand curve. So the only thing we need from the sales tax is that it's varying. So not all the states have the same sales tax. The question now is whether or not sales tax is exogenous, which is it decided outside of the model itself? So our model is the demand function is explained by an intercept, a slope, and the change in price plus everything else. So the sales tax here sales tax should be uncorrelated with the residual. So sales tax should not be correlated with any of the other variables which has an effect on the quantity demanded other than the price itself. So here the correlation should not be 0. So there should be a relationship between the sales tax and the price. And this relationship doesn't need to be causal, but may be only statistical. So there's a correlation but no causality. But in our case, the sales tax has a direct effect, a causal effect on the price itself. One question here is the correlation between sales tax and the residual. So if this is 0, then we say that sales tax is indeed exogenous. Because sales tax is uncorrelated with the residual in the demand function, but price is correlated with the residual in the demand function, we can use sales tax to extract the portion of the price which is not correlated with the residual in the demand function. So our first stage in our two-stage least squares estimation is to obtain the fitted price based on values of the sales tax. So this is just a regression, and you obtain an intercept and a slope because you regress the logarithmic price on the sales tax. And remember that in our case, sales tax does not need to be in the logarithms because we don't need to look at changes in sales tax rather than levels in sales tax and how it can explain the changes in the price. And now we have the predicted values. I will just remove these because it's clutter. And we use these fitted values, just store them, and then you can use them in the second stage. This is the second stage where you regress the quantity on the fitted price. And now remember that the fitted price is not correlated with the error term, which means that this slope is unbiased. And this slope is the causal effect of a change in price on the change in quantity. With our data, we run these two regressions, the first step and the second step, and we obtain the regression results. So this is pi naught hat, this is pi 1 hat, and this is beta naught hat, and this is beta 1 hat, right? So what we said that sales tax should be correlated with U equals 0, right? So there should be no correlation between sales tax and the population error term in the demand function. But we said that this slope should be different from 0. And we can see that because here we have the standard error of the slope, which tells us that we have a t-value of around 6, because we take the estimate, the pi1 hat, divided by its standard error to get the t-value, with a null hypothesis of pi1 population term equal to 0. Okay, so we know that, or we assume that the correlation is with u is 0, and this slope is actually statistically significantly different from 0, which means that we can use these fitted values of price that we obtain from this first regression. And these fitted values we use in the second part of the regression. And here we use the fitted values of the price to explain the change in quantity. And we don't care about the intercept in this case because we only care about the causal effect of a change in price on quantity. And because we get 1.08 and it's significantly different from 0, we find that this demand for cigarettes is elastic. And it's elastic if beta 1 greater than 1, and it's inelastic if beta 1 less than 1. Because what does this tell us? It tells us that the absolute value, it should be. Okay, so it tells us that if price increases by 1%, then the quantity changes even more than 1%. It changes more than the price. So if the price increases by 1%, then the quantity decreases by 1.08%. But why is exogeneity difficult to satisfy or to detect? It's because the residual, the population residual U, is unobserved. So we cannot just run a regression of sales tax on U, or just easily find the correlation between sales tax and U, because we only have numbers for sales tax. But what we can do is to use logic and theory to decipher whether or not sales tax might not be exogenous. And one reason sales tax might not be exogenous in our case is that it might co-vary with the average household income in the state. So for example, average household income in the state is a variable which might affect the demand function for cigarettes. So if you have higher average household income, then cigarettes become relatively cheaper, and this will increase the demand for cigarettes. And if sales tax and average household income is then correlated somehow, then sales tax and the residual, the U, would be correlated. So for example, if income increases, then the states will get more income tax, and hence they might lower the sales tax. In this case, the sales tax and the income would then be negatively correlated, which would violate our assumption, and our estimated price would be correlated with the residual U.